Alright guys, so this is the video for section 6.2, and here we're going to talk about the natural base e. So basically just what e represents in math. But before we go on to new stuff, I want you guys to go ahead and do this warm-up. This goes back to section 6.1 in the compound interest formula. Now, if you don't remember that, go back in your notes. Here it is. Okay, you have it, we've done it, but go ahead and do this. And in this example, we want to know how much money we'll have if it was compounded semi-annually, quarterly, monthly, and daily. So you should have 4 different amounts when you're said and done. So go ahead, pause this, do that, and then we'll come back to it. All right, hopefully you've worked all this out. And when you have, you should have gotten these answers. So semi-annually, you got 78.28. Quarterly 78.31, monthly 78.32, and daily 78.33. So what you should find is that the more times we're compounded yearly, the bigger the profit is, or the more interest you gain. However, with the same time and same rate and the same principal, that number is relatively small. Or maybe I should say that interest, the difference in the interest is relatively small. All right, so now we're going to get into the natural base e, or we just call it e. And the one thing I want you to notice is that e is a number. E is an irrational number. In parentheses, I'm going to put it is not a variable. Okay, so anytime we hear the word e, it's just short for 2.718, so on and so forth. This number is very important when it comes to limits, which you will study greatly in probably pre-calc 2, but especially in calculus. But just know that this is a number that's used over and over, and it's seen over and over again in several different problems. So I like to kind of think of this as pi. You know, anytime we see the symbol pi, we know that that automatically stands for 3.14, so on and so forth. Same thing with e. Anytime we see lowercase e, we know it stands for 2.71, so on and so forth. Okay? So e is called the natural base. And its e comes because it is Euler's number, or some people call them Euler, some people call them Euler. It just depends. You hear them both ways. And that's actually the guy that kind of discovered and published this that kind of made it well known. But that's kind of irrelevant here. All right, let's look at example 1. Okay, now we're going to treat these no different than we did last chapter with our exponents. So e to the 3rd times e to the 6th, remember, is just e to the 3 plus 6, which is e to the 9th. Okay, when I have a fraction, guys, I like to separate them. So 16 over 4 times e to the 5th over e to the 4. Okay, well 16 over 4 is just 4 times, well, e to the 5th over e to the 4th. Remember, when we have a fraction, we subtract them. So 5 minus 4 is just e to the 1st, or just e. So this should reduce just to 4e. Okay, last but not least, remember, this exponent goes to everything in here. Okay, so this is like 3 to the 2nd power, and then e to the negative 4x to the 2nd power. So 3 squared is 9. E to the negative 4x is negative 8x. And we should know that we don't like negative exponents in the numerator, or we don't like them as it is. We need to simplify them. So we would move this to the denominator to make it positive. So 9 over e to the 8x would be my answer there. All right, so let's look at example 2. It says, tell whether each function represents exponential growth or exponential decay. Then we're going to graph the function. Okay, so when I look at this, the number that's being taken to the x power is e. And remember, this e is roughly 2.718. Okay, now remember, from section 1, we learned that if this number is greater than 1, which it is, we have exponential growth. okay? And if it's less than 1, we have exponential decay. So if we graph this, would still cross at 0, 1. If we plug 1 in there, it'd be 3 times almost 3, so somewhere around here. And we know exponential growth just looks, and I didn't connect the dots very well, guys, but something like that. All right, let's look at this one over here. Okay, so it's e to the negative 5x. Okay, so I'm going to rewrite this as e to the negative 0.5 to the x. I'm going to come over here. Do I have more room? Which is just 1 over e to the 0.5 to the x. And if I put 1 over e to the 0.5 in my calculator, I get roughly 0.6065 to the x. All right, this number here is clearly less than 1, so this would be where we'd have exponential decay. Okay, and if we graph that, it'd be like here, here, here. So it looks something like, and then go almost straight up. Because this section's so short, guys, and it's so important, I highly suggest you do these monitoring progress. So go ahead and pause this video, work them out. It shouldn't take you more than 2 or 3 minutes to get all 6 of these done, and then you can check your answers against mine. All right, guys, so this is what you should have gotten for your monitoring progress problems. All right, guys, so here's the last of the problems for this section's notes, and there's one more formula which is right here, and once again, you will need to know this. Okay, so this is the formula for continuously compounded interest. Okay, so compound interest is the formula that we used with 6.1, and that's A equals P times 1 plus R over N to the NT. That's compound interest, okay? This one is continuously compounded. So in order to use this, it has to say somewhere in the word problem that it's compounded continuously, okay? That's how you know when to use this and when to use this. If it's compound interest, it'll give you, it's compounded quarterly or annually or semi-annually, okay? This one will say compounded continuously on it. So that's how you know when to use these two things. All right, so let's look at this question. It says you and your friend have accounts that earn annual interest compounded continuously, okay? That tells me we are using this. A equals P E to the RT. Once again, my P is my principal, which is my starting amount. R is my rate, and my rate, usually I have to convert it from a decimal, or from a percent to a decimal. And my T is the time in years. Okay. So it says you and your friend each have accounts that earn annual interest compounded continuously. The balance A dollars of your account after T years can be multiplied by, so this is your account. It is A equals 4,500 e to the 0.04 t. Okay, the graph shows the balance of your friend's account over time. So this here is our friend's. Which account has a greater principal? The graph shows the balance of your friend's account over time. Which account has a greater principal and which has a greater balance? Okay, so greatest principal first. So our principal is 4,500. We start with 4,500. Our friend's principal starts with 4,000. Okay, so our principal is $500 more. So we start with more money. I'm missing a zero there. $500 more. All right, which is a greater balance after 10 years? Okay, so when t is 10, so 4,500 e to the 0.04 times 10. Okay, I get roughly 6713.21. Okay, now my friends, if I go to year 10, here's 10, I go up right there, and it looks like it's roughly, I don't know, 7,200, just above 7,000 it looks like. So our friend, although they start with less money, has more money, about $500 more, after 10 years. He must have had a better rate than we